This will require a bit of calculation, so let's start with this section. We start with the equation for the total power, and so if we want to find the maximum angle, so what we do is we differentiate the equation for power with respect to delta. All right, so this one, the sine delta will become cos delta, and here you have sine 2 delta, it will become cos 2 delta multiplied by 2. All right, and you end up with this equation, right? And for you to determine the maximum possible angle, right? So you equate dp d delta to 0, and you solve for delta to get the maximum angle. All right, so as you can see there, I've equated this equation to 0. And you end up, when you substitute the values, you end up with an equation in this form. So it's cos delta m plus cos 2 delta m. So two components equal to 0. And I've used trigonometric identity, which is cos squared delta is equal to 1 plus cos 2 delta m over 2. So you make cos delta 2m the subject of formula. You end up with 2 cos squared delta m minus 1, and I've replaced that there. Okay, so you end up with a quadratic equation in the form where cos delta m is your variable. Okay, so solving this quadratic equation, I've written the base equation there for you to remember. So you use the solution for quadratic equation here to solve for cos delta m, and you end up with two solutions. And as you know, cos of delta m lies between minus 1 and 1. So obviously one of the solution is not valid, and this will be the one that's valid. And from there you can solve for delta m, which is 76.79 degrees. Okay. So given the value of the maximum angle, then we can go about solving for each of the variables that you require. So that's IQ, that's ID, right? And once you've determined IQ and ID, you can work out the resultant magnitude of the current, right? So that's the square root of ID squared plus IQ squared. And once you know the current, the load current, you can also work out the maximum apparent power in per unit, right? So that's 3 EI, right, is your maximum apparent power, right? And I've converted it to the actual value. Okay, so that's your base power, which is 1.5 divided by 3 is your base power multiplied by the actual power here, and you end up with 2.832 MVA. So that's the maximum actual apparent power of the machine. And also, if we want to work out the angle, so tan of this angle, which is your, if you go back, you remember, it's basically the sum of phi plus delta, right? So tan of this angle, you can determine it using IQ and ID, ID and IQ, take the ratio, and you can work out what is phi plus delta. And once you know that, you can also determine the maximum power, right? So that's substituting in the original equation for maximum for the power and inserting the value that you worked out for the angle, maximum angle, and you can work out the maximum power. So that's the active power, that the maximum active power the generator can produce. And you can also work it out in actual value. I've converted it by multiplying by SB to get the actual maximum active power of the generator. Right, so from this value that you've obtained here, which is the maximum power per phase, you can also work out the power factor. Okay, so you know that your three-phase power is 3 EI cos phi. So that if you multiply this by 3, you'll end up with your three-phase active power. And from there, you can solve for phi. Okay, and as you can see, um, in this question, we were not sure what is the power factor at which the machine is operating. Okay, so with the equation that we are using here, where we've got phi being equal to 49.86, so there are two possible solutions here. Okay, so if the generator was operating in leading power factor, when you take delta minus phi, you're getting 49.84. If it was operating in lagging power factor, if you add the two angles, so adding phi plus delta is giving you 103.74, which means that this is the incorrect solution here, right? So the one that's correct is this one, where we've confirmed that this angle here is 49.84, and hence delta is 76.79, and at this maximum power, the machine is operating in leading power factor mode. And we can also determine what is this power factor by taking the cos of the angle, and that gives us 0.8914 leading, right? And once you've done that, you can basically draw the phasor diagram for this operating point where it's in leading power factor mode. Okay. So here I've basically solved for the new values for ID and IQ, inserted all the angles, and worked out what is the drop across XD and XQ, right? And then basically draw the full phasor diagram. Okay. So just to recap, initially, when we looked at the initial phasor diagram in part A, the machine was operating in lagging power factor mode, and we drew the phasor diagram. And when the machine we were asked to find out at what angle will the machine operate at maximum load angle. So we worked that out, that angle, which we found out to be 76.79 degrees. That's the maximum possible angle of delta. And from the calculation, we worked out that the generator has to operate in leading power factor mode to achieve this particular load angle. And we worked out the power factor of the machine, and as well as drew the phasor diagram for leading power factor mode. Right, so do you have any question for this example? You can unmute and you can ask any question. Okay, so we'll start with a second example, example two. Okay, so in example two, we basically just exploring the this powerful per unit system, how it can be used to basically determine or analyze a salient pole machine. If you basically are given the d-axis and q-axis synchronous reactances in per unit, and basically without much information, only being given the power factor, right? We can basically analyze the entire machine, drawing the phasor diagram, and also determining the excitation voltage E naught. Basically, once we are given the operating point, meaning the how much power is the machine delivering and at what power factor. Okay, so so given just q-axis and d-axis, as well as the power factor, and given that it's operating at rated power, we will basically analyze the entire machine and draw the phasor diagram for this particular operating point, okay, which is full load, so meaning a rated apparent power at zero point 0.8 power factor lagging, and we will draw the phasor diagram. Right, so if we look at example 2. So in example 2, as I said, they've given us xd and xq, right? So now to determine E naught, right? The step one, I've basically written the angle, which is phi, given the power factor. And we know that it's lagging, so the angle will be negative for the current. So the current is operating at, so being full load, it's 1 per unit, right? The magnitude, and the angle is minus 36.87 from this power factor given. The machine is operating at rated terminal voltage, so your terminal voltage E will be 1 per unit, and as it's the reference, the angle is 0. All right. So next step is to determine what will be the load angle at this particular operating point. So how to get the load angle? We use the equation tan delta is equal to this equation here, which is specifically derived for a lagging power factor generator, salient pole generator. And I've substituted the values for the terminal voltage, the stator current, and the q-axis reactance, and the power factor. Okay, so you end up with this particular angle delta being equal to 19.44 degrees, and from there, if you know what is delta, you can also work out the magnitude of the induced voltage. So this is the same equation we've used in the previous question. E naught is E cos phi plus ID xd, and can replace ID with I sine phi plus delta, since we know the machine is operating in lagging power factor mode. So you can replace ID by this component here, which is the magnitude of the current and the angle phi and delta, right? So we know what is delta, so we can substitute in here in this equation for these two components and then solve for E naught. Okay, so as you know, the machine is operating in motor mode. So the induced voltage will lead the terminal voltage, which is the reference, by a certain angle. So here that angle is 19.44 and it's positive, okay, because it's leading the terminal voltage. Right, so this is your induced voltage in per unit, right? And you're also required to work out what is ID and IQ from the equations that we've presented. And from there, you can draw the phasor diagram for the generator. Okay, so you start with the terminal voltage and the current, and then current I, remember, you resolve into two components. One is IQ along E naught, right? And the second one is ID, which is perpendicular to IQ. So it's a 90-degree behind IQ. Right. So I've drawn the phase diagram for a lagging power factor salient pole generator. And as you can see here in this question, the resistance of the stator was neglected. So from E, you just add ID XD and IQ XQ, and you get basically E naught. Okay, so you need to be able to basically derive all the values on the phasor diagram, right? So as you can see in salient pole machine, the phasor diagram is a little bit more complex as compared to cylindrical rotor. So you have a few more phases that we've added, which are IQ and XD, and sorry, IQ and ID, and then you have IDXD and IQXQ that has been basically splitted into two components because of your two reactances. Okay, so adding all the three phases give you E naught, and that will be your terminal voltage. Okay, so as you can see, from this example too, if you're only given the d-axis and q-axis of the machine in per unit, and you know what is the rated uh, basically power of the machine, you can also solve for basically the equation that's representing the generator. Okay, so I'm going to basically look at the one final example for today, which is example 3. All right, so in example 3, where we've been given a certain machine where the open circuit terminal voltage, okay, is provided versus the field current. So that's your saturation curve. And you've been given the d-axis and q-axis reactances. In this question now, as you can see now, the parameters are given in actual values. So the voltage of the machine is the rated voltage is given, and the d-axis and q-axis. And again, we are neglecting the armature resistance, all right, and we've also been given the mechanical losses of the power. So the first part, asking us to determine what is the corresponding field current and draw the phasor diagram using actual values. So draw the phasor diagram using actual values when basically the motor is operating at full load and it's drawing a certain current of 300 amps at a particular power factor of 0.8 leading. Okay, so this is a question that's now looking at the salient pole motor, where our phasor diagram obviously will change to accommodate for motor operation. And so let's go through the steps. Right, so we are given the power factor, and so we can determine the angle phi, right? So cos of phi is 0.9 and sine of phi is 0.4359. Okay, so that's your two angles that, two components that you will use in ID and IQ. And the terminal voltage is rated at 480 volt line to line. So the phase value will be your line to line value divided by √3. And next step is to determine what will be the load angle, okay, for this particular operation, where your machine is drawing 300 amps from the mains at a particular power factor. So using this equation, tan delta is I times x cubed cos phi plus E plus I x cubed times sine phi. So I've substituted those values into the equation to solve for the load angle, delta, right? So once you are able to work out delta, you can also work out ID, because you require ID for your solution of the induced voltage. Okay, so ID is I sine phi plus delta, and from our analysis in the previous cases, we can substitute the value of phi as well as delta, and then look at the current that's being drawn, the axis current, which comes out to be 172.2 amps. Okay, so if we worked out the current ID, we can then work out the induced voltage. As you can see, it's E cos delta plus ID XD. So substituting, we can determine the salient pole machine induced voltage, right? It's E naught, and that comes out to be 325.2 at an angle of minus 9.185. Okay, so I've also worked out IQ, so that will be I cos of your the sum of basically delta and phi. So that's your phi and that's your delta, and you get basically your IQ. Right, so drawing the phasor diagram, I've basically worked out what is those two phasors, which is IDXD and IQXQ. So when you start from the terminal voltage, minus IDXQ minus IQXQ, you get E naught, okay, which is what we've worked out here, right, 325.2. And so we have to draw the angles phi and delta, and remember the current I will basically result in itself into two components, and the first component is your IQ, okay, and your second component is ID. Right, so I've worked those values out and inserted them in the phase diagram, and let's look at the next part. So once you've determined the field current and draw the phasor diagram using actual values, the second part is motor's full load power is due to the field excitation. Okay, so I looking at this, it looks like it's 8, 9. Okay. So part 3. This is part 2. Okay, let's look at the question for part 2. The maximum torque that can be applied on the motor without pulling the motor out of synchronism when the field current is reduced to 0. In this part, we've looked at part 2, the power that's due to the field excitation, and that's the power due to the saliency. Okay. Oh yes, so we were asked to work out the fraction of the power due to the field excitation in respect to the total power that the machine is basically absorbing. So you take in your field excitation power, PF divide by the total power drawn. So that's your field and your salient power together, and multiply by 100, and you get the percentage of your field excitation power in the motor. Okay. And the last part, telling you that we've reduced the field current to 0. Okay, so the power that's being supplied by the motor is due to saliency only. Okay, and when the machine operates in the salient due to the saliency only, as we discussed in machines 2, the maximum power will be basically at 45 degrees. Okay, so that's for with salient power on only. So then you can use that concept basically at field current being equal to 0 and your field power is 0. Obviously, then the total power can be worked out at delta is equal to 45 degrees. So this is the equation for PS max, right? So I've basically worked out your salient, maximum salient power using the equation, and also worked out the synchronous speed of the machine, right? And the maximum load torque that the motor can produce, which is basically the maximum power at which the motor is working. And I've basically converted it to 81.145 Newton meters. So that's your load, actual load at maximum operating condition for the this particular mode of operation, where your field excitation is dropped to 0 and the power is due to the saliency only. Okay, so as you can see, when the motor is operating at this particular operating point, the value of the line current TL max is the torque. The maximum torque is 814.5 Newton meters, right? And that's basically is greater than the rated current that's specified. And hence, if your motor operates in that particular mode of operation, you can find that TL max is is exceeding your rated power, and hence it will have excessive current that's passed through the motor at this particular operating condition. Okay, right. So in the next part, so we worked out the fraction of the motor that's due to the field excitation. We worked out the maximum torque that can be applied to the motor without pulling the motor out of synchronism when the field current is equal to 0. Last, we determine the motor efficiency. All right. So let's have a look. This is your equation for the developed power, right? So it's your output power, and will be equal to the sum of the field power and the salient power together times this efficiency that's given to you, and you can work out the output power. And the input power comes out from your equation where you have 3 EI cos phi to get the input power for the motor. Right? So by specifying those values, E and I, you can solve for the power absorbed by the motor. Okay, and also we can work out the efficiency. So that's P out over P in, and you'll end up with 95%, 0.99. Okay, so that's it for today. I'll give you the floor to ask any question if you have for the 3 examples that we've looked at today. And on Monday, we will basically again go through some of the questions that are outstanding on the example. And we will also look at a few more questions. Right, you're welcome to ask any question. Please unmute yourself.